for about 5 minutes.
Okay. Well, let's chat for 5 minutes. If that's okay with everyone.
I'm being live recorded, so I'm not chatting anymore.
Alicia, have you managed to set the scope up yet? Oh, we lost her.
No, she's there.
She's just muted. She doesn't. Maybe she doesn't realize she's
Yeah,
muted.
she didn't hear me.
What did I do?
No, I asked if you actually had a chance to set the scope up yet and do anything with it.
No, I have not. Because I have to clean it too. I started that. So.
Okay.
But.
Alicia,
Yeah.
what's your title? Even if you can't say what your project is.
I am well, it's a long title, but I am
The longer the better, man. That means you're very important.
I'm a principal systems engineer, which technically becomes IPTL/CAM.
That was another acronym, which I'm not a
Integrated product team lead, cost account manager. So
Gotcha.
I help lead products under the program.
And you work at JPL?
No, not anymore.
Okay, all right, never mind.
You know, she went to the other place that she can't say.
Oh, I know.
Can't tell
I
you
know
short.
of several other places, but I think the one there's a very famous one.
Well, let's get started.
Really cool one.
Why don't we start the Los Angeles Astronomical Society General Meeting for April 11th, 2022.
All right.
Welcome, everyone. Do we have any new members right off the bat? Justin and Bill,
Yep.
why don't you guys each kind of do just a short introduction, tell us who you are, how did you find us, and what do you want from us? What are you trying to do here?
Just looking more into amateur astronomy, and I always had an interest. I was at the University of Arizona. I had a roommate that was a PhD candidate in astronomy, and so I learned a lot from him about astronomy. We had the opportunity to listen to Dr. Bach talk about his Bach globules. So it's been a long time, but the continuing interest in astronomy, space, stars, etc. And so looking around for different clubs, I found a number of websites that list a lot of clubs, and I found this one, and I've lived in Pasadena most of my life. So I thought, yeah, this seems like a good plan. You guys seem to have a good program, and I'm looking forward to learning.
Right. Well, if you're in Pasadena, then it's a short drive to come down to Garvey Ranch and hang out with a bunch of people there and look through a telescope, a couple of telescopes, and bring one if you have one. Do you have a telescope of your own?
I've got some giant binoculars,
Great.
and I'm looking forward to a star party.
Great. Well, bring your binoculars to Garvey and set them up and show people stuff. Okay. And who else was there? Justin.
Yep. My name's Justin. I moved out to Los Angeles like a year ago. I've always been super into space, but I recently bought my first telescope, and I had tried testing it out once, and I was struggling pretty hard, and I was trying to look for people to get advice from on how to use it. And I came across this group, and Andy had invited me out to Garvey Ranch. I went there like 3 weeks ago, maybe, and everybody was super nice and helpful. And I applied for a membership shortly after that, and I've been using my telescope a lot more. And I'm just hoping to learn as much as I can about space.
Well, you're in the right place, and thank you very much. This is good to
What
hear.
kind of telescope?
It's a Celestron. I bought it off of a website called High Point Scientific.
Sure.
And I forget what the exact model is, but I've got a 10 millimeter and a 25 millimeter and a Barlow that I've been trying to fool around with. I live over in Los Feliz, right by the observatory at Griffith. I actually brought my telescope up there at like 4 o'clock in the morning a few days ago because I saw that the planets were out around at that time to try to see if I could get them in there. Marginal success.
See, now we know you're new based on how you pronounce Los Feliz.
Yeah, I figured that was good.
Well, it only gets better.
I saw probably more coyotes than planets through my telescope.
I don't know if we have any big updates. I guess we can go to the committee meetings because most of the information that are updates are in those committee meetings. So we could start with, I don't know, let's start with Mount Wilson. Tim, I think I saw Tim here. Are you present and available for a Mount Wilson something? Did I see Tim?
I don't think Tim's here,
Tim's
Darryl.
not here today.
Oh, okay.
Oh, by
Okay,
the way,
well,
I posted the link for the drawing, so.
Oh, that's right. He told us he wasn't going to be here. He's got a meeting at Carnegie this evening that he had to go to. Well, for Mount Wilson, it is open and running. They've put out their schedule on their website that it's listing the concerts, and I think they just released a couple of dates for public ticket nights. So if you know people that want to go that aren't members or can't get into one of our 60-inch nights, they can go to a public ticket night. And on the public ticket nights, I think these are both what they call hyper ticket nights. So when you buy a ticket for this, you go back and forth. You can look through the 60-inch and the 100-inch telescope on those nights. So you can look for those on mountwilson.edu website. Let's see, what else do we have?
April 30th.
Lockwood, Kevin, are you up on Lockwood? I don't think we have anybody from the Lockwood committee here.
No, I don't think we have anything. Wait, hold on. No, I don't think we had anything new to say other than it was very cold and very wet.
Okay.
Well, actually, I can give a short update. We cleaned out the trailer, so it's it's ready for use now.
Yay!
Oh, okay. And also, we did get the Starlink up and running.
Yeah, Starlink
talked
is
about
up
that
and
at the
running.
board meeting, but the general meeting doesn't know that. So if you're going to Lockwood, we have a much better internet connection there now.
Yeah,
So-
we went from about barely 10 megabits downlink to about 75, and about half a megabit uplink to about 5 megabit uplink. So it's pretty speedy now.
Good. So we love Starlink and we hate Starlink. So there you go. Curtis, you want to tell the general public what's happening with Ford coming up? We're about ready to get that going, yeah?
Yeah, the ski area is officially closed for the season. Ford will have an event. We will open up Ford for the Memorial Day weekend. And Joe and I are going to try to get up there in the next couple of weeks to survey the situation. Although I did talk to Greg Thomas, and he said everything was, he was up there a few times in the last couple of months, and he said everything looked good up there. So we're not too far away from ready to open it up to the club. But I think we may get a little snow tonight, but I mean a little snow tonight or tomorrow, a little light dusting, but in general, the road's not in too bad a shape, but the gate is still somewhat locked, but I think that'll be taken care of because the ski area is closing. That's it on Ford.
All right, cool. Greg, you got a scout update for everyone?
Yeah, most of you are familiar. If you're not, we run an astronomy merit badge for the council scouting in the LA area. And we're finally back on this year for in-person classes at Garvey Ranch this summer. Our flyer will be going up on the council website in the next week or two. We usually fill up in the first night or two once it goes up because word spreads very quickly. And I try to keep the number of students down to about 15 so that the scouts have more chance to do hands-on work and it's not quite so chaotic. It's a good number. We have a nice classroom set up there. I will get the dates out in our communication flyer. They are June 15th, July 13th, and August 10th. They're regular Wednesday nights at Garvey Ranch. So if you're go there anyway, you'll see us set up in the classroom. If you're interested in coming and helping out, as simple as bringing a telescope and setting up on the lawn. There's a couple of half-hour viewing sessions, and the scouts are required to learn, not just look at an object through a telescope and keep notes, but learn about what type of telescope it is and what an eyepiece is and how focus works. And so the club's been really helpful with turning out a little bit. I mean, we don't need, it's not a Griffith Park. We only have 15 scouts and usually some parents, but it's super helpful. And if you'd like to help out in that way or any other way, you can always get a hold of me. If you haven't read the requirements of the astronomy merit badge, they're not trivial. Actually, the scouts have to do a variety of drawings and learn a variety of things about observing, as well as astronomical objects and then physics and some stuff about careers and things like that. So it's a really fun night. There, and I'll get the word out on the communications wire here in the next few weeks. So thanks a lot, Daryl. I appreciate the opportunity.
Great.
And if anyone has any questions right now, you know, I'm not.
I have a quick one, Greg.
Go ahead.
Would an astrophotography setup help at all, or is that just doesn't fit with that program?
No, it fits completely. It doesn't even have to necessarily be doing anything great. One of the requirements is they have to learn about, I think, 5 different instruments that are attached to telescopes.
I've got about 12.
Well, there you go. But they have to learn things about the ER spectrum and also things about radio astronomy, and the scouts are interested in the computer thing. So, you know, you get a few scouts come by if you've got a camera set
What
up.
about H alpha?
Well,
Yeah.
Greg, that's what I was going to say. Is that actually makes sense because I'm a narrowband guy, so the only thing you see is what's on the computer. But that's why I asked if it would fit in. That sounds like something I might be willing to do a couple of times over the summer if it's helpful.
That
Yeah, I'll
would be
send
great,
you-
Richard. I'd like to see you have a setup at Garvey one night. That'd be really good.
Absolutely. I mean,
Okay, Daryl.
yeah, if you set up
Solar.
on the lawn,
Yeah.
the scouts will be out for about a half an hour to do their observing session. And, you know, if a scout comes up and asks, can I look through your telescope? Give them a chance to say, well, this is a digital astronomy setup, and, you know, tell them a little bit about it. They're supposed to come back and provide notes about their observing session. So I'll get a chance to see if they learn
Right.
anything, but that would be great. And thank you.
Okay, no, that'd be cool. I think, yeah, I'll get back to you on that because that.
Okay.
All right.
I'll
guys
send you
keep
the
that-
dates.
You guys keep that going, and you know how to get a hold of everyone here. So,
Cool.
David, can you get us an update on outreach and the 30th, the Star Party?
Yes, the board has approved, if I'm correct, right, Daryl?
Yep.
The Star Party at Mount Wilson. Okay, so we are officially on for our first Star Party after COVID at Mount Wilson Observatory, and we will be up at the upper level parking lot. And Curtis, you can chime into this as well, or anybody who's been there. You can get there early in the daylight hours, like I believe about 5:30, if I'm correct. And my understanding is the public will be invited to this one. And we're hoping that the Cosmic Cafe will be open. And there will be, let's see what else. There's a gate. So hopefully Evan will be there, and myself, and at least one other person to get this thing properly positioned to where the people that are going to the 60-inch will go to the 60-inch, and the people that are coming to the LAS Star Party will be assigned to go up the parking lot area to the upper parking lot, and that's where we will stay for the evening. We're still getting some particulars on that, but I'm sure that hopefully will be on the website. Is that correct, Spencer?
I don't think it's going to be on the
Yeah.
website, but Evan will put it on social media as well as Ed Dempsey.
Okay.
We can get them to put that out. So what we reach with the social media will be the extent of the public reach, which is about right for what we want to do for the size that we have there. It worked very well a few years ago when we were doing that. So we're doing these
Normally we have
on our concurrent 60-inch nights. So the club has a 60-inch night that night as well. So we're making this a concurrent Star Party with that. They're in the upper parking lot. 60-inch people will come and we'll go and look through the 60-inch. But there's a good way. You know, the 60-inch people know that we need to gather outside the gate and come in as a group, and some of the other people that are coming up may be going in and out of the gate. But we'll take care of that at the time.
Right. Okay.
Okay, great.
So
And then there's also
everyone is invited.
okay. And then do we have everyone that we need for the outreach on next Thursday?
As far as I know, there's going to be an outreach this coming Thursday at Farragut Elementary School. It's located in Culver City. I believe I got to look at the time, but I believe it's about 5. I have to look. 6 o'clock, 7 o'clock. Tim was the one that told us about that. So I can hold on.
There's some emails going around, but it's like 6 to 9.
Oh, okay. If we get 6 to 9, and they're for 5th graders, so there'll be a bunch of 5th graders. So we'd like to have at least 7 or 8 telescopes over there to be able to show the kids. And we'd love to have you join us.
So any people who want to do that,
is there a way to find the?
I'm sorry.
Is there
Go
a
ahead.
way to find the directions?
Yeah, David, can I have people contact you that want to do this can you send them directions in the school and all that on your email?
Let's see here. I'll put it up on the site here. I'll put it up on the chat.
On the chat?
For everyone.
Okay, so
Yeah.
I'll put the address on the chat and the time.
The time and everything.
Yeah, do the whole information on there.
Yeah, I'll do that right now. I'll be right back.
Okay, so
And
that'll be there in a
that's it,
few
right?
minutes. That's fine. Take your time. We'll do it. It'll get there.
And somebody wants to confirm the Star Party in Mount Wilson is April 30th.
That's
correct?
correct. That's correct. It's Saturday night, and our 16-inch night is that night as well. And there's still openings on that night on the 30th too. So if people want to sign up for that, you can reach me at Mount Wilson Coordinator at LAIS.org. And there's also, I'll put my email address in the chat as well. And there's openings for all of the rest of the 60-inch nights for the year as well. So let's get them booked up. We were clouded out on the first one, so we still haven't had the real first one yet. So there was one more thing I wanted to say about Lockwood. Lockwood, the shed that was donated to us by Carson. Chris, I saw Chris, he's here tonight. Chris Valdivia and I went over there and started taking that apart. It's a roll-off roof shed. It's a tough shed that was been modified to a 2-piece roof that rolls off to each side, and it's a good-sized shed. We're going to take it up to Lockwood, and I think we're going to put the Takahashi in it, possibly. But it's going well. We were able to get quite far on the dismantling, and I think the next phase, which needs to be in the next few weeks, I'm going to check with John when he gets back from vacation. But the next phase is going to probably take 6 or 8 people to commit to be there that can lift something, because we're going to have to roll those 2 roof pieces off of the rollers and onto ourselves to let it down. So we will be catching that off of the rollers and setting it down. So we're going to need 6 or 8 people to do that twice. The rest of it, once we get those off, should come apart pretty quickly. We've got it kind of mapped out what we need to take off, and we've taken off everything that we can already. So that should go pretty well.
Daryl, I'm sorry, what was the date that you were trying to do that, or do you not know yet?
Don't know what the next date is. We did the first one, we took care of that. Chris and I took care of all that. The next one, I don't know. We got to coordinate 8 people. So whatever date we can get 8 people to commit to within the next few weeks. I know it has to be out of there by some time. They're doing some work in that yard and that needs to be gone. So we're well on the way. There's one more committed trip with the trailer that we're going to put everything in, and we can do it. So that's a big announcement for Lockwood. Other than that, I think we're pretty good to go. I guess we could have our speaker start. Spencer, you want to introduce our speaker? I think you have the
Sure.
blurb in front of us, and I saw him that he's here, so that's fantastic. Thank you.
So I've got
There he
his.
There he is.
Hi, Ken. How are you? Thank you for joining us.
Thanks for having me.
So excuse me. So this is you can see Ken's bio on your screen. So he's a project scientist for the Mars 2020 Perseverance mission, and he's going to speak to us about the I guess you're on the you're at the crater. So I'm just going to leave it at that and turn it over to you.
Okay. Thank you very much.
And actually, so how do you prefer? Do you want we can, in the past we've had people mute and then ask questions later, or post them in the chat, or some speakers will actually have people ask questions during the presentation. However you want to work it.
Why don't we try people asking questions, because it makes it a little more conversational.
Mm-hmm.
If it looks like it's not working, we can switch back to just using the chat. But people should feel free to ask questions verbally if they want. I'm happy to turn it into a conversation instead of more of a lecture.
Okay.
Is that okay?
Perfect.
That's really great. Thank you. Also, there's like 43 or 44 people here too. You don't see everyone on the screens.
Yeah. Okay. Great.
Nice audience. Go ahead. Thank you, Ken.
Okay, I'm going to stop sharing, so you have control of the screen now.
Okay. So let's see if this technology is going to work. And are you seeing the proper screen?
Mm-hmm.
Yes.
Okay, great. Yeah, so I am the project scientist for the Mars 2020 Perseverance mission. I'm also a geochemist at Caltech. I've been working on the Mars 2020 project since its inception, since 2014. And for the first 7 years of that, I was working with the engineers to help explain to the engineers who were building the spacecraft what science actually needed. And I'll tell you, this was a fascinating thing for a scientist to do, to participate in just seeing how one builds an incredibly complicated piece of hardware. So I'll tell you a little bit about that as we go along. The project scientist role is primarily focused now on leading the science team. So we're on Mars. We have more than 500 science team members, and we are every day deciding what we're going to do with the rover and what samples we're going to collect and that sort of thing. So it's a very interesting daily interaction with lots of people, lots of engineers, lots of scientists, and with Mars. We've been on Mars for 406 sols, Martian days. And I'll tell you, we have now completed
I think we
might have lost Ken.
Mm-hmm.
It might be frozen because his screen is not moving on the side either.
No, it looks like he's frozen.
Let's let him go out and come back in. He'll know.
It's a dirt race at Bristol, baby.
Somebody's TV is on in the background. somebody's not muted.
Yeah, that's better.
Okay, let's see. I think he's dropped off completely now.
Okay, if his other screen's gone, he's probably
Yeah. Mhm.
He's a smart
reconnecting.
guy. He'll figure it out. He just has to relog into the setup.
It's amazing this all works anyway.
Yeah, it's a long connection from Mars anyway, so you got to expect.
I was gonna say we can land a rover on Mars, but we can't keep a connection to the internet.
Well, I wouldn't take an AT&T rocket to Mars either.
Good point. Good point.
Again, somebody's TV is in the background there. Someone, please check if you're not muted. Everybody should be muted except for our speaker.
That isn't actually what we were doing.
Yeah, but my understanding is we'd only unmute with a question.
Yeah. Okay. Well, I haven't seen him. Let me.
He may not be aware that he's disconnected, so somebody better call him.
Yeah, unfortunately, I don't have his phone number. I just got his email address. He should know that we're disconnected, though. I mean, he should get a warning on his side. Okay, let me just see if I can't ping him real quick.
Yeah, he may just have lost everything though. So
Yeah.
Yeah, he could have lost his cable router or anything, you know. Was Windows decided to update? Who knows?
no, Windows only decides to update when you are trying to do astrophotography for the first time at night. And then it decides it's going to install an update on you.
Yeah, that's another one in there.
Yes, and then the drivers don't work after the update.
Yeah.
As astronomers, we're all very, very patient. We take a long time to do things. It's okay. We'll give them a few minutes.
Yeah, my wife used to say, don't you have a systematic way of doing things? Because you're always complaining that something else went wrong. And I say, yeah, it's always something new that goes wrong.
Yeah, that was an Air Force saying, it's okay to make mistakes, just make new ones.
Well, let's see.
Okay, let me just try this one more time. Let's see. Unfortunately, I can't find an email address for him. Or I mean, a phone number for him.
Okay, so in the meantime, let me bring up the next total solar eclipse in 2020.
Oh, wait, here he comes.
Okay, good. No eclipse.
Am I back?
Okay. Yes, you're back.
Hey, you're back.
Wow, this is like bad timing. Sorry about that.
Not a problem.
All right, let's see if I can get this thing going again.
No. Are you locked up again? You're not moving.
Kevin, are you there or did you lock up again?
No, I think he's gone again.
Gone again.
Okay.
This may sound strange. Strange was carrying. I was drawn. Oh, and when this stitch was something, you inspired the Lexus to me. Well,
Yeah, I don't see him on anymore.
Ernesto, you need to mute. Thank you.
Okay, while we're waiting, I'm going to post the link for the drawing again.
And I also posted my email for the Mount Wilson information.
And I'll take advantage of this to put in a pitch for the dark sky, preserve dark
Petition.
sky petition and change.org.
Sure. Put it in the link. We have a
So we're at 688 people who've
Right.
signed, and the Audubon Society is going to have a meeting on the 13th, and they're going to share the link with their membership. So the goal is to try and get as many as we can. We're trying to set up something with the Board of Supervisors and see if we can get some traction on it. But let's see, I'll get the link for the dark sky petition in just a minute. So if you haven't signed it, please sign it. And if you signed it, share it with somebody else, because the more people we can get on this, the more traction I think we'll have.
Is it free to sign?
Huh?
Is it free to sign the petition?
It's free to sign the petition, although they will ask you to make a donation, and you may or may not want to. We don't really see the money for the donation, but what happens is that if you don't make a donation, then they actually use that money to sort of advertise the petition and push it out to more people. So they have their own marketing. I'm not sure how that works, but anyways, I just posted the link for the petition there. So there's nothing involved, you don't have to donate or pay anything to sign it. Just sign it and share it with anybody else. Because like I said, the more people we can get to sign this, I think the more weight we'll carry when we see the, when we finally get to meet with the supervisors.
So let me go back to where I was going to talk about the eclipse. In the background, one of our members over the past probably almost 2 years has been putting together an eclipse place for himself and a group of where he works, and he is an LAAS member, and LAAS members are welcome to get the information from him and show up where he's got this place set up, similar to, some of you probably were at the last total eclipse, and a lot of the new members certainly probably weren't. But similar to before, he has some kind of a deal going with a high school in Ingram, Texas, which is only a few miles, not even a few miles, I think, from center line on the eclipse. I think he's got it set up so that you can come and camp for a couple of nights on the site, and he's also got a list of a lot of the places around there that you can either camp at or reservations at. However, almost all commercial places that you can rent or go stay to will not take reservations more than 1 year in advance. So you can't call, Best Western down there and say, I want to book this night. They won't do it. So, and a lot of people are aware of that. So I think the thing to find out is when will they take the first booking, and if you want to, do it that way, to be on top of it. Because I think a lot of people are going to be much more aware of this one because of so much publicity on the last one that was just a few years ago. So a lot more people are going to be aware that it's a really cool thing to do.
And it looks
So
like
I
we
will
have
put-
Ken back.
I'm sorry?
Ken's back.
Yeah, I'm back. There's something strange going on. Whenever I advance the slide, it crashes. So I'm going to try this one more time, and if this doesn't work, I'm going to go to Plan B. I don't know exactly what's going on, but you can hear me okay, and you can see this.
Right.
Okay. So I'm going to watch you guys. You're still moving. Every time I start this one, I lose you. But okay, here we go. I'm going to tell you first about what I think is probably the thing, if you know anything about this mission, is what you know about, which is the landing. And I just want to show you that this is a really spectacular event, and it was recorded with a number of cameras on the spacecraft during entry, descent, and landing. So I want to show you a little bit of this really spectacular piece of video. And I want to set the stage for the... Did I lose you again?
No.
Oh, okay. You guys got to keep moving because I keep looking at it like, am I talking to myself? You're going to see a lot of this landscape here. So I just want to set the stage. This big feature here, which I'm going to tell you a lot about, is the delta. And for scale, this is 1 kilometer across. Very conveniently, this crater is 1 kilometer across. These cliffs are 40 meters high. And we had thought the most likely place to land was in this area here we call the landing strip. That is, in fact, not where we landed. We actually landed over here at the X. You're going to see in the little piece of video I'm going to play from the spacecraft, you're going to see the cliffs of the delta. You're going to see this crater called Hahutsa. And you'll see this very sand dune rich region, which we call Seta. And then you'll see this area over here, which is filled with craters and boulders. So let me just move on to that one. Okay, so the trick of entry, descent, and landing on Mars is that we need to drop velocity very quickly. This is on a ballistic, spacecraft is on a ballistic trajectory to Mars. So there's no orbit to slow down first. And so we have to go through a series of steps to basically slow down sufficiently that we land softly. And the first step, which is shown in the little drawings at the bottom, is just an aeroshell. So the rover and what's called the descent stage are all packaged up inside this aeroshell. So this aero brakes and steers the spacecraft, essentially flies the spacecraft through the atmosphere until it has slowed sufficiently that we can deploy a parachute. So we go on, we deploy the parachute. We no longer need the front part of the aeroshell, so we drop that away. This allows us to take images from the spacecraft of the ground. We stay on the parachute for a while, dropping velocity. If we landed just with a parachute, we would hit the ground too fast. So the terminal velocity on a parachute is too high to land successfully with just a parachute. So then we move on to the next stage, where the descent stage, which is essentially a set of rockets attached to the rover, drops away from the parachute. And the video I'm going to show picks up there. Now, there's one more thing that has to happen here is this entry, descent, and landing scheme allows us to avoid hazards. And we do that by taking images from the spacecraft and comparing them to onboard images, which we have already indicated where it is safe to land and where it is not safe to land. So we essentially just do a registration between an onboard map and a map that we took from our image that we took from the spacecraft, and avoid any no-go zones. So this video picks up right when that phase begins. It turns out we were going to land in a place that was not good. And so that's the delta there. That's a Hahutsa crater. We would have landed in this area here, and the spacecraft made its split-second decision that we were going to go way over to the other side. So here's the crater-rich and bouldery terrain. And this is at an altitude of about 2 kilometers. And we're dropping, this is in real time, we're dropping very quickly. And soon you will see the dust start to get blown away from the surface. So that's the interaction of the rockets with the surface. There we go with that. And then we cut to the actual video from the spacecraft. So you see the rover literally being winched to the ground on its wheels. And as soon as there's slack on the bridle, these bridles will be cut with a pyrotechnic bolt. And the descent stage, the rockets will actually just.
Oh, lost him in the middle.
Right when it was getting good.
Well, that's
That's exactly when that video is not supposed to cut off, right?
That's bad news.
That's exactly.
So what happened?
Everyone is holding their breath.
That's the transmission lag from Mars.
I hope it's all been okay.
Looks like he's still on.
No, he's gone now.
Oh boy.
So while we're waiting, I guess somebody asked if they need to sign up for the Star Party at Mount Wilson. I think the answer is no, right?
You mean the parking lot Star Party?
Yeah, right.
The concurrent Star Party in the parking lot, in the upper parking lot, is just you show up. And if you're a member and you have a telescope, you can bring your telescope and set it up. It's a great place to look at things because it is a lot darker up there than it is down here. Especially
Talking about everybody's talking about Mount Wilson right now, not Lockwood.
Yes, that was the question? Yes.
Yeah, right. Yeah, the question is Mount Wilson Star
Mount
Party.
Wilson Star Party in the upper parking
all right.
lot. Yeah. All right. No, you just show up on the 30th. The Mount Wilson is open that day as well. It is a Saturday, so if you wanted to come up earlier in the day and just enjoy Mount Wilson, walk around, look, be up in the trees, and then stay until it gets dark and stay for the Star Party in the parking lot. That's a great evening, right? And then you're coming up in the daylight, so you see what's going on. It makes it a little easier to leave, knowing where you are.
Right. Looks like Ken's back on now.
Okay, but no, just show up.
Yeah.
Hey, I'm really sorry. I have no idea what the problem is here. Can you hear me?
Yeah.
Yes, we're fine. We just talked about something else when you're not here. That's fine.
All right. So we landed successfully, obviously. Wouldn't be talking to you otherwise. We landed here at a place we call the Octavia Butler Landing. And this area
I don't see your other screen yet, though.
That's because I forgot to share it. I could probably give this talk if I didn't share the screen. It wouldn't keep crashing.
It's okay. We're fine. There we go.
Okay.
But wait. You left us halfway through the descent.
Okay. All right. I'm going to risk running this again.
Okay. I'm sorry. If this crashes, then it's my fault.
Okay. Here we are coming down to the ground. Did you see this part?
Yep.
Yes.
Yeah. We got this far.
And here goes this, what's called the sky crane maneuver. We winch the rover to the ground.
Got that far. Lost you about here somewhere.
Okay, the wheels touch down. The tension goes off the bridles. The bridles are cut with pyrotechnic bolts. And then the descent stage flies away and crashes. We're done with it.
Great. Woo, there it goes.
Oh, we made it. Thank gosh.
Okay.
Yeah. And let me tell you, that was a spectacular moment. That video actually arrived in the control room at JPL the night we landed, and the engineers, when they saw that, they loved it because they built this thing, had no idea what it would actually look like, and so it was a spectacular moment. So we landed at this place, Octavia Butler Landing, that is right on the edge of this area that's filled with sand dunes, and this area here filled with boulders. So it's just this very narrow little region that was safe. And it turns out, you'll see in the images, it's very flat here. You can see why the rover picked this, spacecraft picked this as our landing site. This is actually an orbital image. That's Perseverance there. And these butterfly patterns here, that is where the rockets actually blew dust away from the surface and exposed a slightly lighter colored material below. So great moment, very successful landing. Everything went about according to plan. There were a few strange things that happened during EDL, but all good. The spacecraft landed successfully and no damage. I just want to say a few words about the Perseverance, or the Ingenuity helicopter. This is part of the technology demonstration set that Perseverance carries. This is the first rotorcraft to fly on another planet, and it was a remarkably successful demonstration of the technology necessary to fly a rotorcraft on Mars. The key challenge here is that the atmospheric pressure on Mars is only about 1% of Earth's atmospheric pressure at sea level. And so this is not just your hobby shop drone. This is has a very large pair of counter-rotating blades. Its original design was to fly 5 or 6 test flights to demonstrate that flight could happen on Mars. It has worked perfectly, and we just completed today the 25th flight of this helicopter. It moved from a technology demonstration to a scout for the rover, and this is turning out to be a really remarkably successful demonstration of a capability that is now turned into something that we use to, for example, look for interesting scientific targets and to plan routes for the rover. So that's been great. I can talk more about that in the question period if you want to ask about it. So the Perseverance rover is built on the same design as the Curiosity rover, which was launched about 10 years ago. We have a few new capabilities. A major new capability is the ability to collect core samples. I'm going to tell you about that. That is one of the key objectives. We have new science instruments, and we also have new wheels. The Curiosity wheels got punctured by rocks pretty quickly, so they completely redesigned the wheels. The mission's goals are, at the highest level, seek evidence of ancient Martian life. And I'll tell you specifically why the word ancient is in here. This is not a life detection mission. We are looking for ancient Martian life, so I'll tell you why. Preparing samples for return to Earth. This is, I think, the biggest objective of this mission. We are tasked with collecting 43 small tubes with Martian samples. And NASA and ESA are jointly now discussing how they're going to bring these samples back by future missions. So Perseverance is not tasked with getting them back to Earth. It is simply collecting the samples. So I'll tell you how that might work. And then we have this very broad directive to enable the future by demonstrating technologies like the helicopter. And also we have inside the rover an instrument that demonstrates the capability to convert Martian atmospheric CO2 into oxygen as a potential propellant for future exploration of Mars. That has worked remarkably well also, but I won't talk more about it. So why are we looking for ancient life? We are looking for ancient life because the present surface of Mars is inhospitable to all life as we know it. And so that's all we can say is that we don't think that there is anything, well, there is nothing that we know about on Earth that could survive under the current conditions on Mars, which are too cold and too dry and have too much both ultraviolet and cosmic ray irradiation for anything that we know about on Earth to survive. But it wasn't always that way. So I show you this picture from the Curiosity mission, which I think nicely shows this place is cold and dry. But to a geologist looking at these rocks, they are very suggestive that Mars was once very different. What you're looking at are sedimentary rocks, and most or possibly even all of the sedimentary rocks that you see here were laid down in either a lake or in a river system. So prior to about 3.5 billion years ago, Mars climate was very different. And this is, there's no doubt about that. We don't really understand why that's true. The major climate event that happened about 3.5 billion years ago took Mars from a condition where there was liquid water on the surface. That tells you it was warmer and it was wetter. And it tells you that the atmospheric pressure had to have been higher because otherwise the water would have boiled. So the point is that life in the distant past on Mars is much more plausible than life in the current environment because it's warmer, it's wetter, and there's less radiation thanks to the atmosphere. There was also a magnetic field which shielded the planet from charged particles. So if one is to look for life on Mars, rather than trying to find life as we don't know it, the approach that's being taken by the Perseverance mission is to look for life that is recorded in rocks that were deposited in this distant time period on Mars. So this is an artist's conception of what Mars might have looked like at this time period, about 3.6 billion years ago. There's a lot of controversy about whether there was a northern ocean. I'm not sure I have a strong opinion one way or another. There's very little evidence for it or against it, but it is very clear that there were many, many lakes and river canyons carved by surface liquid water. So it was very different at that time. So in this idea of looking for life in the distant past, it makes sense to ask the question, well, what would you look for? And all we can do is use Earth as an example of one and ask, what was life on Earth like at this time? And coincidentally, the oldest undisputed evidence of life on Earth is from almost exactly this time period, about 3.6 billion years ago. So you're looking at one example of this ancient terrestrial life. This rock that you see here, it's in a very small outcrop in Western Australia. There's almost no terrestrial rock record from this time period. Those rocks have been destroyed either by plate tectonics or simply by erosion. So what do we see in that life? Well, this is that evidence. What you are looking at is a kind of a rock called a stromatolite. And a stromatolite is produced when organisms that are growing at the boundary between water and mud in a shallow lake or sea, when those organisms form a mat, and that mat actually disturbs the surface of the sediment and binds it together, making this characteristic bulby pattern. And one of the reasons we know that this is a biogenic rock is that we can see these things alive today. And so on the right, you see an image that is of a living stromatolite. So this is a microbial mat that has produced these structures. These are exposed at very low tide here. It's an unusually low tide. Usually these are underwater. So this rock you see on the left is a 3.6 billion year old example of this thing that we see living on the right. So if this is one kind of thing that we should be looking for, and it motivates the point that at 3.6 billion years ago, life on Earth was still very primitive. In fact, the kinds of things that we are all familiar with as fossils, things that we might take our kids out to go collecting, like shark teeth and trilobites and fern fossils, and none of those advanced structures appeared until about 650 million years ago. So that's actually 3 billion years after this rock record on Mars. So it doesn't, using this example of one, it makes more sense to look for microbial life than to look for advanced life. Of course, we would be very excited if we found a dinosaur bone, but it is not something that we think would be very likely. So one point I want to make here is that this ancient life on Earth at 3.6 billion years ago occurred in a shallow lake or sea. Where Perseverance has gone in Jezero crater is a shallow lake from 3.6 billion years ago. So to me, this is actually a really important and interesting statement that we have two planets at the same time where there are environments that are as similar as we can tell right now. We don't really know much about how what the climate on Mars was like, but at least for some of the time, it was warm enough and wet enough to have a lake. So we went to this place called Jezero crater, and this is Jezero crater. This is the rim of the crater. It's about 45 kilometers in diameter. The rim is about 1 kilometer high. And the big feature that you see here is the delta, where a river that reached the crater flowed into the lake. And we know there was a lake here because the delta is produced when the sediment that is being turbulently suspended by the flowing river hits the slack water of the lake, and the sediment drops out. So this is a clear indication that there was a lake here. And we know that that lake was once full enough to actually flow out through an outflow channel. That allows us to estimate how deep the water was. The water was at least 100 meters deep. So you should picture a lake 45 kilometers in diameter, at least 100 meters deep. This is a very large lake. This is not a puddle. So this is an artist's conception of what this might have looked like. We don't know exactly when this was. I use the figure about 3.6 billion years. The reality is that age is determined by counting the number of craters that are present. I suspect that most of you are familiar with how this works. But on Mars, the uncertainty in the production rate of craters is so large that that 3.6 billion year age has a inaccuracy of potentially 500 million years in either direction. Could be 4.1 billion, could be 3.1 billion. And it's sort of amazing that that encompasses almost a quarter of the history of the solar system. That's how poorly we know that the actual age is on Mars. So this is the target for the Perseverance mission, because it is a appears to be a very habitable ancient environment for us to go look at the rock record to see if there's any evidence of ancient life in it. The delta not only tells us that there was a lake present, but the delta also is itself a very habitable environment. And it also is extremely good at preserving evidence of life. So I grabbed this image. I think this is a delta that I think is somewhere in Alaska. It shows a number of features that you'll see in following slides. One is these distributary channels. This is the way deltas work. They tend to flow out in different directions and produce lobes as each channel flows and then chokes itself off. So you'll see some of that in the following slides. It's also a good place for things to live. You can see that with these, presumably these are some kind of algae growing in the mud. And then that mud entombs, rather gently entombs the organisms that live in the delta. So it has a high ability to preserve evidence of life that was once within it. So this is a great kind of target. It's the main reason we went to Jezero, is that it has this delta. So I'm going to show you what we learned on the ground in our first year. And remember, this is the front of the delta. These cliffs are about 40 meters high. We landed here. Our first desire, the highest value target, was the delta. Well, it turns out that this area that we call Seta is absolutely untraversable. It is filled with sand dunes. No way we're getting across it. So we couldn't quickly go over to the delta, and we decided that instead we would explore the area around here, which we call, just broadly speaking, the crater floor. And I'm going to show you some images of two places that are associated with the delta. One is the delta front. One is this feature called Kodiak. So what you see on the delta, these are those distributary channels that I was telling you about. You can see quite a few of them moving off in different directions. Some of them go way over here. Kodiak is a remnant of one of those distributary channels that has been isolated by erosion. So it's like a butte. If you go out in the desert, you see these all over the place. You see isolated remnants of high standing rock that were once attached to other high standing rocks that haven't eroded. So this is an erosional remnant. And that actually tells us the delta was once much larger and has retreated by erosion. So I'm going to show you pictures of these two features, Kodiak and the delta front. And then I'm going to show you some pictures from around the landing site. So this is Kodiak. This is probably my favorite image that we've acquired on the mission so far. It is a spectacular exposure of a delta. So I showed you that image of the Alaskan delta. Picture cutting a slice into the mud down to 40 meters and picking it up and looking at it edge on. That's what this is. The features that you see are, you could put these in a textbook. They are so compellingly the way a delta behaves that it's just very straightforward to understand. The tilted layers are the very front of the delta, where sand and mud cascade off of the front in the lake. That causes the delta to prograde, which means to move outward into the lake. It grows and moves out into the lake. And therefore, the stuff on the top, just like you see on here, on this image, you're seeing that the river gets longer. And so imagine that these sloping units are being produced very down here at the bottom. These rocks at the top, these fine layers, these are produced by a river, just like the sand here, if you looked at it in cross section, would have these fine laminations in it. So textbook example of the delta. This area here in the foreground is Satan. This is the area that we cannot drive across because of the dunes and the boulders. The more surprising result that we got was from the delta front itself, where we saw this feature here. So what you're looking at here is a series of boulders, and below these boulders are fine layers, which we presume to be river deposited sand. And there are lots of these big boulders. This is a blow up of that area. This boulder is 1.5 meters across. You don't get boulders that big transported in a delta because the water is slowing down as it's in the placid water of the lake. So what these features are almost certainly telling us is that sometime after the main delta formed, there were floods when the lake level was lower. And those floods were large enough that they were still able to sustain transport of meter scale boulders. That's a massive flood, kind of like this image that I have on the lower right. So this is telling us something about the history of the filling of the lake, and it drives home one of the interesting points that is worth thinking about. This crater has been sitting there as a low spot in the topography for 3.5 billion years. It probably got filled more than once. It's a very potentially complicated set of events superimposed on top of each other. This is a classic problem in geology, that events get superimposed on top of one another. But this is 3.5 billion years of events superimposed on top of each other, which is kind of a hard thing to get your head around. So,
good question.
Yeah.
Is it possible that boulder was ejected from one of the other impacts?
Yeah, that is that really good question, and we have thought a lot about.
The other second question is simply those slanted layers that you showed in the previous slide looked like they happened, and I'm not a geologist at all, but it looked like they happened at different times because one's higher than the other.
Yes, two great questions. They are exactly the questions that we talked about on the team. Let's deal with the delta first. So the delta grows with these lobes, and it basically grows out on top of itself. And I can show you experiments that are done in laboratory flumes where you can actually see this forming the sloping layers, forming more flat layers, and then it moves out and deposits more similar layers. So there's not much question about this, but this is a series of events as the lake appeared to either be stable in size or possibly even getting deeper. So that's one interpretation of this. And then the other question about these boulders, one of the things I should have mentioned is this shape that you see, this kind of lens shape. You see this all the time in sedimentary sequences on Earth. It is the shape of a river channel. That's the first observation that's important here. This is exactly the shape of a river channel. The second thing is these boulders are all very rounded. They have been moved somehow, and impact ejecta is not typically rounded. We've seen impact ejecta around some of the craters we've driven around. It's angular blocks. So this is, I think, quite reasonably interpreted as water transported.
Thank you.
Okay, so now moving on to the crater floor. The images that I just showed, we had those in hand within the first 2 months of the mission. So they were a first big success that got us excited about what we're going to find on the Delta. But then we did this out and back traverse from the Octavia E. Butler landing site to this feature, which I'm going to show you, called Artubi Ridge, and into the area called Seta. So I'm going to show you pictures first from here and here, and then I'm going to show you pictures from Artubi Ridge. So this is the area around the landing site. You can see why we landed here. It's pretty flat. It's not just sand or regolith. The area that we landed on has these, what we started calling flagstones. These are rocks that are right at ground level, and they have this kind of whaleback morphology. They're smooth, and that's very indicative of what's going on here. These rocks have been planed off at the ground surface. It's not a coincidence that they're right at the ground surface. They have been planed off by blowing sand. This is another example of what 3.5 billion years of just sitting there will do. Even tiny amounts of wind abrasion multiplied by a lot of time will polish rocks off. So these rocks have been ground down to the surface. And you can also see, I don't know how, if your screens are big enough, but you may be able to see fluting here, these lines. This is another characteristic of wind erosion called ventifacting. And many of these rocks, I imagine if you touched them, they would feel extremely smooth. Just like if you go out in some places in the Mojave, you'll find the ventifacted rocks that are just beautifully fluted and smooth. In the background, lots of boulders. So you can see why we didn't land there, and you can see why we're not going to drive through that. These boulders are meter scale, so no way we can get through this. I think all of us were surprised by how rugged this bouldery landscape is, and also by how little evidence there is for the origin of the rock. So a central question that we ask is, what are these rocks? How were they produced? And the rocks that I showed you from Gale Crater, where they were very well layered, a geologist looks at that and says, know what that is. Those are sedimentary rocks. Well, these rocks, they don't speak very loudly about what they are. And it's even worse than that. These rocks are coated with dust. That's the origin of the orangey color. That is just dust all over the rocks. When they're gray, the dust has largely been blown off. When they're orangey, they have Martian dust on them. And as we discovered, these rocks also have a coating on them of some material that makes it very hard to see the structure of the rock. So we struggled to understand what the origin of these rocks were, literally for 8 months. And in that 8 months, the engineers were bringing new capabilities online on the rover. So we arrived with not all of the capabilities ready to go. And 8 months in, we developed the capability to abrade the rock, to grind off the surface of an area that's about 5 centimeters across. And that's what you see here. And the image that you see on the right, when this image came down, it was like, oh yeah, I know what this is. After months of not knowing, what are these rocks? Are they igneous? Are they sedimentary? Are they lava flows? What are they? this image came back, the one on the right. It's like, yep, it's another textbook example. So let me set the stage for that. So this is one of those flagstone type rocks. If you compare it to the area around the landing site, this other site is maybe 2 kilometers away from this region here. Here, these rocks look very solid, don't they? They look like, you know, they're not falling apart. Well, for reasons that are not that interesting, but probably in hindsight not that smart, we decided that this rock was going to be the first place that we attempted to take a sample and use our abrasion tool. So we reached the robotic arm out and we abraded. So this is a patch about 5 centimeters across. This is what it looks like when we blow the dust away. We have a little compressed gas source and we can blow the dust away. And you see a bunch of things. If any of you are geologists, I hope you look at this and say, that's an igneous rock. That looks like a gabbro. And if you don't know that word, a gabbro is basically like a granite, which I assume everybody's familiar with what that looks like. A gabbro is just has more magnesium in it to a good approximation. A gabbro is a rock that crystallizes slowly such that you get big crystals. And so these big black and white crystals, they look, just in this image alone, they look like an igneous rock. But there's more. First of all, this rock is brown and with brown staining all over it. And if your first reaction is, well, it looks like this rock is rusting, you'd be right. This rock has experienced interaction with water that has altered it and released iron in some way to make this staining that you see. There are big holes in it. And there's this crevice that you can see. These are not gas bubbles in a lava flow, for example. This looks like places where material has been removed, probably by interaction with water, possibly by interaction with wind, we don't really know. And then there's even one more feature, if you look closely, you can see that there's 2 shades of white. And in particular, there's this very bright white, which looks kind of diffuse. These grains have pretty sharp boundaries, but this looks, you know, sort of diffuse and very bright white. So that was interesting, trying to understand what that is. The rover has on its robotic arm a wonderful new capability for Martian exploration, and that is the ability to measure elemental compositions and map them across an area that is about 5 millimeters on the side. So what you see is looking into that abraded patch. So this area that you see in the pink box is about right here. So we took this instrument which uses X-ray fluorescence to measure the elemental composition. And we've picked a color scheme. We actually get all the major elements in the rock, but we've picked a few elements that allow us to understand.
You do have a spectrometer.
Say again?
I said, so you do have a spectrometer. You can.
We have several. We got X-ray fluorescence. We got Raman. We got infrared. We got everything. I'll show you some of the results from pretty much all of those instruments.
Thank you.
Yeah. So these minerals, based on their chemical composition, are absolutely the minerals you would expect in an igneous rock. Pyroxene, plagioclase are the major constituents. The area in red is this kind of brownish staining. Unsurprisingly, it is rich in iron. So this is pretty much a slam dunk. This is an igneous rock. Whether it is a basalt, that is a lava flow that runs out on the surface of the ground, or if it is an intrusive rock like a granite that cools slowly below the surface, is a matter of debate. But these rocks are undoubtedly igneous, and they have interacted with water. Then we discovered that these white patches are actually salt minerals. They are minerals like calcium sulfate, magnesium sulfate, and sodium perchlorate. These look like they are places where water has penetrated into the rock and then evaporated.
That could also be rocket fuel, right?
It could be. It better not be where we are. We didn't bring any perchlorate with us. Perchlorate has been detected elsewhere on Mars. It is. I will say it is very confusing about why it's there. We don't understand how it forms, but it is, for present purposes, it is an extremely soluble salt. And the fact that it is still here tells us that this rock, after that perchlorate got added, it has not seen any more water because it would have removed the perchlorate. So the youngest thing in the rock is the perchlorate. So we have a pretty interesting story here. This is an igneous rock that has had multiple kinds of interaction with water, forming these iron oxide materials and also forming salts. So we decided we would sample this rock because this is the kind of rock that if you brought it back to Earth would be really interesting because, for example, we could date it. So we could actually do a much better job at than 3.5 plus or minus half a billion. A rock like this brought back to a terrestrial lab like the one down the hall from me at Caltech could date this rock to precision, probably 3.51 billion plus or minus 0.01. So we can potentially really nail that in a terrestrial laboratory. And it looks like an ancient habitable environment because on Earth, organisms would live in a rock that is altering this way. This is probably a rock that is altered beneath the surface. This rock was not exposed on the surface at the bottom of a lake. This is probably interacting with groundwater. And when you have elements like iron with multiple redox states, the iron in the minerals is iron +2. The iron in the oxides is iron +3, just like rust. This is a energy source for microbes to take advantage of that redox gradient. So this looks like a potentially habitable ancient environment in an igneous rock, very valuable as a potential sample to bring back to Earth. So we wish to collect it. So let me run this video of how we collect the sample. But before I do, let me tell you what you're going to see. So the rover has on the robotic arm, this robotic arm is 2 meters long. It has this device at the end called the turret, which weighs 70 kilograms. So think about that for a minute. 70 kilograms mounted on a 2-meter lever arm. This is a pretty tricky operation. The instruments, for example, the one that showed the X-ray fluorescence results, they are mounted on this turret, and we can point them at the ground. We can rotate this device to bring, say, this instrument. This is the Sherlock instrument, which uses Raman spectroscopy. We can point that at the ground. Then we can rotate it, and we can bring the drill to the ground. So interestingly, our wonderful science instruments are mounted on a rotary percussive drill. So they get vibrated pretty hard, which is an interesting engineering challenge. So we can place the drill on the ground and acquire a core. The core looks something like this. It's about the size and shape of a piece of chalkboard chalk and weighs about 15 grams. This white tube, the sample tube, is actually inserted into the drill bit, and we core right into the tube. So this tube is an exquisite piece of hardware. All this tooling that you see down here so that we can manipulate it with the robot. It is ultra clean. We need to make sure that it had no terrestrial organic matter in it. So this is a very special piece of hardware. We core right into the tube, and then we seal the tube. So each sample gets its own sealed tube to ultimately be brought back to Earth in. So let me show you how this works. So this is a really nice animation. So the rover at this point has arrived at a target. We want to drill this rock. So we extend the robotic arm and rotate it around so that the turret is pointing the rotary percussive drill at the surface, and the drill already has a sample tube in it. So these are stabilizers that contact the surface, and then we rotary percuss into the ground. using a very clever mechanism, we break off the core and hold it in the tube, and then we ingest it into the rover to seal it. So there's that sample tube. And now the big reveal, this incredibly complicated piece of hardware called the adaptive caching assembly. So this is a really sophisticated robot that takes the sample tube through a series of stations that allow us to understand what we've got. So for example, we can measure how much sample there is. Did we actually get sample? We take a picture of it. We then ultimately seal the sample tube hermetically. So it's an absolutely gas-tight seal. And then we take this and return it to one of these little like beehive chambers from which the tube was taken. So we pulled it out, we filled it, and we return it. And then we carry the sample away. So on board the rover is where we are presently storing our samples, but I'll tell you that's not ultimately where they're going to go. So that's what is supposed to happen. And this, as you might imagine, because this is such the key thing that this mission needs to do is collect these samples. The first time we tried this, there was a lot of anxiety. It's just unavoidable. This is the incredibly sophisticated new thing that we built. Please, please, please make it work. And when we first tried this, let me digress for a minute. We get information from Mars not by direct communication with the rover. The rover, we tell the rover what to do once a day using the Deep Space Network big antenna. We point the big antenna at Mars and it goes right to the rover. The rover doesn't have enough power to talk back to us that way. So instead, the rover talks to an orbiter, and the orbiter with a giant antenna points back at Earth and sends us the information. But it only does that a few times a day. So the day that we sent the instruction to go collect that sample, the rover knows how to do all of that, from reaching out to boring out the sample to ingesting it back in the rover and sealing it. It does that all autonomously. But we get snapshots of that when the rover communicates with the orbiter. And at about 1 o'clock in the morning, many of us got up to actually see this image. So this is exactly what we hope to see. It's a nice clean borehole. It's exactly the way it's supposed to look. And we were pretty keen on it. But the rover hadn't finished sealing the tube. It wasn't going to do that until about 7 o'clock in the morning. So at 7 o'clock in the morning, many of us trooped over to JPL, and we're in the mission operations facility. And the first piece of information that came down that was readily interpretable is the rover is good. It has successfully completed collecting the sample. And so we were like super excited because we had a hole in the ground and the rover said, "I have sealed your sample tube for you." So we were getting ready to high five and declare victory when somebody actually looked at the picture down the sample tube. And that's the image in the lower right. This is exactly what you would see if you were shining a flashlight into an empty tube. That brassy color is the bottom of the tube. And that absence of sample, if you look really closely, you can see some little black specks. There might be, 20 micrograms of material in there. But the volume probe also confirmed there's nothing in there. And let me tell you, this was an incredibly deflating moment because everybody was so keyed up and ready to cheer. And yeah, not so much. So that was very stressful for everybody, very discouraging. And a lot of people wondered, have we built the wrong tool? And the reason I bring that up is just to drive home the point. When you interact with a place you've never been, with objects whose properties are not well defined and not knowable, there's the potential that you will build the wrong thing. And we've seen this in a number of missions where people have done their best to estimate what the characteristics of the material are, and they're wrong. Interestingly, the engineers were quite concerned about this. The scientists were not that concerned because when we collect cores on Earth, this happens pretty often. Core falls apart. And that's what we concluded happened. We looked down in the borehole and there's There's no sample in there. It didn't fall out. But this rock is very altered. And as I showed you in this image, it's filled with holes and cracks and alteration. And so what we concluded happened is this rock just did not have the integrity to hold together. And so interestingly, the engineers said, okay, let's not try this again until we find a rock that we know is very, very strong. And so the science team got together and we decided that the next sample would be one that we picked simply because we knew it would be very strong. So we looked around. That failure that I just told you about was right here. Failure to collect the sample was right here. And we took images over to this feature called Artubi Ridge. It's this very peculiar linear thing. Everything else here is kind of curved and lobate. This is very linear, which tends to suggest some interesting geology. And sure enough, when you look at it closely, this is that ridge. You can see it consists of layers that are tilted by about 15 degrees, providing a really nice cross section and showing us, in fact, that these rocks are layered. That was something that we had been wondering about, again, whether these are igneous rocks or sedimentary rocks. We initially thought, hey, these look like maybe they're sedimentary rocks. But for present purposes in the conversation, we wanted to find rocks that were really hard. Where would you find hard rocks? You would find hard rocks on the crest of the highest piece of topography where the wind has been blasting the rock for billions of years. So find a very resistant rock up on the ridge. So that's what we did. We drove over on top of that ridge. This is the ridge. It's only a couple of meters high. Again, very layered rocks, suggestive of sedimentary rocks now, different from that first rock. And we decided we would go after this rock here, which is about the size of a briefcase. All of us agreed that rock looks really hard. That looks like a rock, if you hit it with a hammer, the hammer would ping off of it because it has been sitting there and any weakness has been eroded away by the wind. And you can actually see the wind fluting in it here, the ventifacting on this rock is very prominent on the rock. And we were successful. We drilled our first 2 holes into this rock, got 2 cores. This is the rotary percussive drill bit taking its victory lap. We take some images to see whether we damaged the bit. It's fine. This is now what it looks like when we peer down into the bore of the tube. So whereas before all we saw was the brassy bottom, now we see this rock, full length core. This is probably about a 15-gram rock. It is in every way that we can tell perfect. And it is also
an accident that it looks like the previous igneous rock.
Haha, yes. Well, so it does, good eye. It is another igneous rock. And to a good approximation, it is the same. It looks like it's a little bit finer grained. The pyroxene and the plagioclase are smaller, finer grained, but it has the same big white salt patches and it has the same rusty staining. And the puzzle is, well, these rocks look really layered and yet they look like igneous rocks. Those two don't usually go together. And I'll be honest and say we haven't yet fully sorted this out.
And you found them quite a ways away, right? I mean,
yeah. So the punchline of this is that all of the rocks, so this is our entire family of rocks that we have now cored. So we failed here. This is this place called Rubion. And the one I just showed you was called Rochette. And that is the cores that are right here. They were called Montagnier and Montagnac. And then we drove into Ceta and we got more igneous rocks. And again, just by looking at the grains in here, if you have any geologic background, yeah, those are coarse grained igneous rocks. Everything on the crater floor is igneous. Big surprise. We thought we were going to find sedimentary rocks because this was on the floor of a lake. And we could tell, remember I pointed out how Kodiak was an erosional remnant? Clearly the sedimentary rocks must have at one point extended all the way out here, but they have eroded away and exposed these igneous rocks below. That's actually good because the next thing we're going to do is we're going to explore the delta. So we're going to get a really good diversity of samples, which is one of the key objectives. So we acquired these cores in our first year. And now, oh, first let me tell you what's going to happen with these samples. I'll tell you what we're going to do after we finish the crater floor campaign in the next little bit. But first, let me tell you how this is going to work, how these samples are going to get back. So the Mars 2020 mission collects the samples. It is not responsible for bringing them back. And many people wonder, like, why wouldn't you just put a rocket on board this rover? And the reason, there are really two practical reasons for this. The number of engineers who know how to build a complicated spacecraft is finite. And you don't want to just hire people off of the street to do this because it's a very specialized skill set. And those engineers were already working pedal to the metal to finish this rover to allow it to launch at the 2020 launch window. So first of all, it's just a matter of having enough personnel to do it. And the second is adding all of that additional complexity would have added to the cost of this rover and would probably make it unsustainable. So rather than do it all in one mission, you solve both of those problems by spreading it out over multiple years. In fact, with Perseverance having launched in 2020, the follow-on missions, which I'll describe in a minute, are likely to launch in 2028. So they're spread out over almost a decade, which makes it much more palatable.
Wait, there's the JWST that ate all the funds. Never mind.
Yeah. We're not talking about that.
I'm shutting up.
It's very true, and well, we could have a whole conversation about why missions they tend to be over budget. I don't think it's anything nefarious. I just think it's the unknown unknowns are unknowable, and they will come back to bite you at some point. So the way the sample return is conceptualized right now, and the missions are now in the earliest phases of development jointly between NASA and ESA, are to have a Mars ascent vehicle, a rocket, that lands with a fetch rover. It's not shown in this image, but either with a fetch rover or a separate landing of a fetch rover to pick up the samples. What am I talking about here? Well, so the samples right now are on board the rover. This is problematic in the sense that if Perseverance fails, if it has some kind of debilitating failure, then the precious cargo can be trapped inside. So as soon as we have a valuable enough collection of samples, we will put them on the ground. Just the tubes themselves, we will lay them on the ground as a target for that fetch rover. So the fetch rover will land, it'll drive over, it'll pick up the tubes, it'll ferry them back to the Mars ascent vehicle. It'll put them in what's called the orbiting sample. It's basically a sphere the size of a basketball, which is mounted in the nose cone of the rocket. This rocket flings the orbiting sample into orbit, and then an orbiter captures it and brings it back to Earth. It's a very elaborate set of steps and is, I think, unprecedented in the complexity in that it involves multiple missions. It involves multiple agencies, multiple, first of all, NASA centers are involved in this, but also a joint operation with the Europeans. Extremely complicated set of things that need to happen to bring these samples back. But the notion right now is that they will launch in 2028 and these samples will get back in 2031. And that's a long time from now. But this process has begun, and it seems to me it's quite likely to happen. The samples that we have collected are really just exactly what the science community wants. And so I think there's a high likelihood that this will actually come to pass. So let me just tell you what we're doing now. We finished this campaign on the crater floor, and we wanted to get to the delta. And at this point, we decided we were going to do what we call rapid traverse, drive, put everything else aside and make time. So the rover has autonomous navigation on board, and you see it operating here. It's driving across the landscape on its own. This all happens in an afternoon. The rover is capable of driving a maximum of about 350 meters in a day by itself. So it actually, you tell it you want to get to a certain place, and it will actually find the route to get you there. So what you see here, every dot is one place where the rover spent the night. When we got to here, we turned it on and said drive, and you can see the dots are very far apart. We set rover distance records here. So it's a 5.5 kilometer drive. We're going to finish this in 30 sols. We're almost done with this. This has been remarkably successful. Over the weekend, we did about a 530 meter drive in one plan. So one instruction to the rover, drive, and it drove 530 meters. It may not sound like much, but Curiosity it would be unusual on Curiosity to do more than 40 meters. So this is enabling of a long drive. Interestingly, as long as I have this picture here, I'll show you. We did this 530 meter drive, and Ingenuity, which is the green dot, Ingenuity had been out here in the middle of Setah. It did a 700 meter flight over the weekend also. So both the rover and Ingenuity set records for distance in a single day on the same weekend. So that's pretty cool. One other thing I want to show you about autonomous navigation. This is just kind of a cool animation of what the rover actually did. And we told it we wanted to go up and see this area here. So we told it we wanted to have a waypoint here and a waypoint here, and then get over to here. And you can see it, finding its way through the rocks. So we don't give it all of the details. We just tell it roughly where we want to go, and off it goes.
But Ingenuity was not the guidance, right? I mean, it was too far away for you to know the lay of the land.
Right. One of the things I should have mentioned is we have these just fantastic orbital images. So we knew roughly what the topography was. The green route is the fastest route that the people who programmed the drives said, this is the fastest route you can take. The scientists said, oh, we want to go over and see these rocks. And so they put in the waypoints to do it on this sort of orbital view. And the rover, it basically counts the revolutions on the wheels, and it knows how far it's gone. So it has a pretty good sense of where it is. And several times along its trajectory, it'll localize itself by looking at the sun. It gets a fix by looking at the sun.
You can't tell from the picture, but is that another crater there?
This here?
No, down in the lower, the lower right.
Oh, this?
Of the image. Yeah, there. Yeah.
Yeah, that is the big feature called Setah. And this, I told you about Artubi Ridge where the rocks are tilting back from it. It looks like in this area here, again, these rocks are tilted back from it. So these are all igneous rocks, but for some reason, it looks like this area here was bulging upward and pushing these rocks away. It's definitely not an impact crater because it has the wrong shape for it. You can see craters in it, but so we don't actually know what the origin of this is.
What are those stripes, if I'm not being too anal?
You mean in here? Is that what you mean by stripes?
I see those, but go back to the most recent image. See those stripes down at the very lower right before the other image?
Over here?
Right there, yes, that's it.
So these are dunes. These are linearly organized dunes, same as up here. That's a very common feature. Then there are these interesting things that you see that look like cracks, which they probably are. how they form?
They look like Rima. They look like moon Rima.
I don't know what that is. So I'll just conclude. I got one more slide. The end of the drive campaign is going to be right here at the Delta. So now again, you're looking at this 40 meters of topography of the Delta. And we're going to drive right up this I want to call it a valley, but that has an implication of flowing water. I don't think that's how this formed, but this little route to drive up
like
onto
Cajon
the Delta.
Pass.
Yeah, it's like Cajon Pass. Okay, a little smaller than Cajon Pass, but there are a bunch of interesting features that we already see. This whitish material that you see, we have a pretty good guess that this is mud deposited on the bottom of the lake that has turned into mudstone that has now been protected by these resistant rocks. These cap rocks are almost certainly sandstone. And then this is probably a stretch for you unless you have a big monitor. the top up here and also all along here and all along here is filled with really big boulders. And those are the flood boulders. So the targets that we want to sample here are the mud at the bottom of the lake, because that's a very habitable environment, and the sands and the boulders, because those came from way up this way. This is the inlet channel into the crater. This is where the river came in. And so the sand and the boulders could have come from as far away as 70 kilometers. We'll never get that far away. And so we're going to let the river do the work for us. Say again?
What's the scale of the image?
40 meters high. And this valley is probably 60 meters across. And this big thing in the back is the crater rim that's a kilometer high. So that's the plan. I am done with the slides that I wanted to show, and I'm happy to answer questions if you have any.
Fantastic. Thank you very much.
Yeah, that was really, really nice. Thank you.
Ken, could I take you back to the geology for a second?
Sure.
My dad was a professor of geography and geology in the seafloor spreading and early continental drift days. I'm just wondering what evidence, and this is kind of on behalf of my father, I'm not an expert, but I grew up with it. Have you found any evidence along the lines of stuff around that continental drift kind of, I don't know, science?
Yeah, so the question is whether there are plate tectonics ever existed on Mars, and I would say there was a very splashy paper that reported results that look like the magnetic stripes that are the key indicator of plate tectonics on Earth on the seafloor. I think that has largely been refuted. There is definitely no indication that there is much in the way of tectonics happening now. If it ever did happen, it stopped a long time ago. There's still active volcanism on Mars. You know, the big volcanoes like Olympus Mons, they have been active within the last few million years. But in terms of having, you know, plates that are moving around, there's no indication of that. There's not the kind of faulting that you would expect from that.
And is the plethora of all the, I mean, you told me about why certain boulders are too round to be ejecta. Is most of these other kind of miscellaneous rocks that we see all over the lake bed here, are most of those ejecta?
We have not seen anything that we are strongly compelled to think is ejecta. So probably the best way to show that is, well, like right here, all of these rocks are they're just eroding out of these small cliffs. And in this area here, we now have convinced ourselves that that these are just boulders.
Yes,
and
that's the image. Yeah, that's a great image.
Yeah. So all of these boulders, we can actually see. I'm going to see if there's one in this image. But the way these boulders get made is the rocks stand, resistant rocks stand proud, you know, above the surroundings. And many of these rocks, if you look at them, you will see like this one is undercut. And it's forming what looks almost like a mushroom in some sense. And this makes a lot of sense because the sand doesn't get picked up very high. So the sand works around the base, and eventually the little protrusion just falls off as a boulder. So this is how we think most of these boulders are made. And like so this one here is probably outcrop. This is probably rock that's intact.
So does the fact that there are a few impact craters in the original image mean that most of the evidence of the impacts are long gone?
When we, from the drive that we did around here, we imaged this region, we imaged this crater, and we've seen images of this crater, not in great detail. They are filled with local ejecta. Undoubtedly, you can. I mean, if I could, I can't zoom in on this one, but if I did, you would agree that this is an apron of ejecta. And in fact, this whole area here has been
I have no idea what I'm talking about. All I was thinking is that you said that it's so hard to date impact crater or impact cratering on Mars, that maybe the rocks of the impact might show some sort of dating.
Yeah. Okay. So a couple of things about that. Indeed, a big impact, much bigger than these, will reset the radiometric dating techniques and will be a good target. For example, when we get over to the crater rim, the Jezero crater rim, this 45 kilometer diameter crater, we expect that we will find rocks that have been very heavily modified by the impact. These impacts, which are only a few hundred meters across, probably have not done that to the rocks. So we can't date them directly. But just by the continuity of the lithology, basically all of these rocks are in family. They're not ejecta from far away. At some level, everything has been beaten up. Like surely some of these little hills that you see, what you're looking at on the horizon here is this area here. So yeah, sure, they have been hit by stuff, but it hasn't moved very far.
So you're not seeing the shocked kind of stuff at the moment.
Yeah, not from these little craters.
Ken, what kind of evidence of life are you trying to detect? Fossilized, maybe subterranean, like a tardigrade or something like that?
Well, so the most likely thing that we would find is microbial life, and you might ask what we would see. And the thing that is kind of the poster child that everybody trots out and said, we're looking for organic matter. And we have a Raman spectrometer, which is designed specifically to detect organic matter. We have detected organic matter in these rocks. That does not mean that organic matter is biogenic. So biology leaves organic remains, but not all organic remains are biogenic. And in fact, we think in the rocks that we have found the organics that they are almost surely not biogenic. So
I think that'll have to be the last question.
Sorry?
Oh, I want to have that maybe be the last question so we can.
Okay.
Okay, great. That was a fantastic. Thanks for taking so much time to take.
Thank you so much.
I'm going a little long. Lost a little time in the beginning. So
Thank you so much, Ken.
Yeah. Thanks for having me. And sorry about the technical problems.
No problem.
That was a treat.
You did a great job. Very informative.
And sign up for the giveaway. We have some prizes, and I see Spencer put that in the chat just a minute ago. So
yeah, there it is. There it is again. So there are only about half the people signed up for the drawing so far.
Good. No, just kidding. Odds are better here.
Yeah.
We'll give everyone a couple of minutes. Thanks, everybody.
Sorry, where do you sign up for the drawing?
It's in the links in the chat.
In the chat.
The one that says drawing link.
I just resent it again just now.
No, I don't see anything.
It should be the last one that popped up.
And thank you for putting up with my questions.
Okay, so let's make the drawing closed.
Okay, so let's see. We've got. I want to give about 30 more seconds, so we'll close out the drawing.
Good.
As you can see, I'm rocking out my hat. I won that last month. Thank you.
All right. Last call. Closing it out now. Okay.
Alicia, how many gifts do we have to give away this month?
6.
6. Okay, great.
All right, drawing's closed, and I'm getting ready to do it now. Just 1 second.
Get the spreadsheet up.
Yeah, hang on 1 second. Let me pull up the. Let me populate the spreadsheet. Okay, hang on 1 second. Now it's my turn to have computer problems.
It's one of those evenings.
Okay, let's try this one more time.
Keep singing, Alicia.
Oh my gosh, you can hear that?
What was that?
Yeah, we heard her singing. Very good job, Alicia. Very nice background music.
All right, here we go. Okay. All right, let me share the screen here. Where are we? Okay, everybody see the screen? All right, let's pop the names in there. Oops. Oops, so much for that. Hang on, let me get the names again.
I'm not sure you're sharing your screen.
Yeah, I'm not sure. I'm not seeing.
Oh, you're not seeing the screen?
I don't think so.
Nope.
Okay. All right, there. You see that one now?
Yep.
Yes.
Okay.
There we go.
Yes, I see it.
All right, now. Okay, let me put the names in there again. Okay, Jose is the first one.
All right.
Oh my gosh, he wins like every single week. No, I'm joking.
I missed one or
Congratulations.
two of them.
Yeah,
All right.
I have your address on Instant Dial. He won an Amazon gift card.
All right. Thank you.
Okay. All right, next one's Pablo.
Hey, Pablo.
Oh, yeah. Thank you.
Oh snap. He won a LAS hat, but I can't remember if he already won one already.
No, I don't have a hat. LAS.
Oh, okay. Okay.
All
I
right.
have a lot of flashlights, but no.
Yeah.
Okay.
In fact, I
Now
have
you
a
can-
flashlight store now, thanks to you guys.
Now you can find your hat.
Okay, next is Greg Thompson.
Oh, Greg just won a laser.
Woohoo!
Hey, good job.
All right. Robert Farley.
Robert won a Celestron Observer's map of the moon.
Ooh, thank you very much.
Okay. Justin Hawkins.
Justin won a red flashlight.
Oh, nice.
All right.
Cool. I like him.
New member got a present. Got a present on your first meeting.
Thank you so
Fantastic.
much.
How many more?
One more.
Omar.
Hey, awesome. Thank you guys.
An item from the LAS store.
Sweet. Thank you guys.
Wait, don't delete it yet. I have to write his name down. Okay, got it.
Okay. All right.
Well, that's the last thing that we do, so we can adjourn and stop the recording, and then people can still chat for a little while.
Right.